The expression of electric field for the infinite plane sheet is sigma over 2 epsilon naught, right? This is the expression of electric field due to an infinite plane sheet, sigma by 2 epsilon. And the direction of the field is perpendicular to the sheet. The direction of electric field is perpendicular to the sheet always. So if you have this infinite plane sheet, this is the infinite plane sheet. The sheet have a charge density of plus sigma. The direction of field due to the sheet is perpendicular to the sheet. So this is the direction of electric field. Okay. So can you plot E versus R graph? E versus R graph for this field. See here, E is sigma by 2 epsilon naught. So this E is independent of R, which means here electric field is independent of position. R is position. R is always position, separation from the field, separation from the sheet. The expression of electric field is absolutely independent. So for this infinite plane sheet, the expression of electric field is sigma by 2 epsilon naught. This we have derived in the previous class. This expression is absolutely independent of R. There is no R in it. So you can say that this electric field is uniform. This electric field is uniform. Uniform means independent of position. Independent of position. Which means if I take a sheet and I say that at a distance of 1 meter, the value of field is 10. At a distance of 1 meter from the sheet, the value of field is 10. So at a distance of 2 meter, the value of field will remain 10. At a distance of 3 meter, the value of field remains 10. Value of field will not change on changing the distance from the sheet. These types of fields are known as uniform fields, and these uniform fields are independent of position. And the direction of field is perpendicular to the surface of the sheet. If I ask you to draw E versus R graph, means electric field versus position graph. Now, since electric field is independent of position, that means on changing position, the value of field should not change. On changing position, the value of field should not change. So this graph would be a straight line. You see, you simply keep on changing R. On changing R, field will not change. The value of field is not changing. So this type of field is absolutely independent. This is known as uniform electric field for infinite plane sheet. Okay, let's solve a question on infinite plane sheet. This numerical is given in NCERT. So you have few sheets. Let's consider 2 sheets over here. This is sheet number 1. And then you have one more sheet. This is sheet number 2. This is sheet number 2. The surface charge density of sheet 1 is sigma 1. The surface charge density of sheet 2 is sigma 2. You're supposed to calculate electric field in between the sheets. Just say, let's calculate field in all 3 regions, in region 1, region 2, and region number 1. Let's calculate field in all 3 regions. The magnitude of electric field due to one sheet is sigma by 2 epsilon naught. Okay, Afroza, let's start from you. We have 3 parts for each one of you. So, Afroza, what is the direction of field over this point due to this first sheet? What should be the direction of field over this point due to the first sheet? It's left way. And what about the field, direction of field in this region due to second sheet? No, it's not towards left. It's negatively charged sheet. The direction of field due to negative charge, it's towards the charge. So for the negative charge, the direction of field would be towards the charge. So in region 1, if we solve region 1, then electric field in region 1 is simply the vector sum of electric field due to individual sheets. That's E1 plus E2. Or you can say that direction of field in region 1 is it's E1, which is sigma 1 by 2 epsilon naught. The direction is to the negative x-axis. So let's say this is minus of I cap. E2, it's sigma by 2 epsilon naught. It's plus I cap. E2 is acting towards positive x-axis. While writing magnitudes, we never consider the nature of charge. Whether your surface charge density is positive or negative, we won't consider that nature. Next, we can take this I cap by 2 epsilon naught as common, and we are left with just minus of sigma 1 plus sigma. So that is the electric field in region 1. If I repeat the same calculations in region 2, Fatma, what is the direction of field in region 2 to this positive sheet? Is it towards right, left, or the direction of
left?
Due to positive sheet.
Right.
It's always away from the charge. So that's towards the right. And what about due to this negative sheet?
Right.
It's towards the sheet. So both are acting towards x axis. So in region 2, the net field is simply the vector sum of E1 and E2. So the net field in region 2 is E1, which is sigma 1 by 2 epsilon naught I cap, sigma 2 over 2 epsilon naught I cap. So in region 2, you can take I cap by 2 epsilon naught as common, and we are left with only sigma 1 plus. So this is the value of electric field in region 2. For region 3, Jubena, direction of field in region 3 due to this positive sheet?
Okay, right side.
It's always away from the charge. No? So away from the sheet is this right hand side. And what about due to this negative sheet?
Left side.
So in region 3, the net field in region 3 is vector sum of E1 and E2. So vector sum of E1 and E2. So in region 3, the field is sigma 1 over 2 epsilon naught. Direction is along x-axis, so that's I cap. This E2 is along negative x-axis, so it's sigma 2 by 2 epsilon naught minus of I cap. So you can simply take I cap by 2 epsilon naught as common. So this is sigma 1 minus sigma 2. Sigma 1 minus sigma 2. This is how we calculate electric field due to infinite sheets. So, okay, so after infinite plane sheet, the next thing is electric field. Electric field for infinite wire. Infinite wire or infinite rod. Basically, for a long one dimensional, instead of infinite, he can use long, a long wire or a long rod. If it is one dimensional, then you can use the result that will be derived. So let's say you have this thing. You have a long wire. The linear charge density of the wire is lambda. This is the wire. A long wire, this wire extends from minus infinity to plus infinity. The linear charge density of this wire is lambda. You're supposed to calculate electric field at a separation r from the wire over this point. Yes, Fatma, sheet was two-dimensional. Yes, sheet is area basically, in area is two-dimensional. You're supposed to calculate electric field over this point due to this infinite thing. Why? So the first step is consider a Gaussian surface. Okay, can you suggest the shape of the Gaussian surface? The appropriate shape of the Gaussian surface for the wire?
Cylinder.
Cylinder. For the straight wire, the appropriate Gaussian surface would be a cylinder. So let's consider a cylindrical Gaussian surface. The radius of the cylinder is r. The length of the cylinder is l. Wire extends from minus infinity to plus infinity. It's a long wire. Practically, long wire means this. Practically, long wire means L is very, very greater than R. Means the point at which you are calculating the value of field, the separation of that point is small as compared to the length of the wire. The length of the wire is very, very large as compared to separation. Then you can say that your wire is a long wire. Because infinitely long wire is practically not possible. When we say that wire is infinitely long, or we say it's a very long wire, that simply means the length of the wire is very large as compared to the separation at which you are supposed to calculate. L is very, very great. So let's consider a cylindrical Gaussian surface. A cylindrical Gaussian surface of length L and radius R. Fatma, can you guess the direction of electric field here? Electric field is along x-axis, y-axis, z-axis. Fatma, the direction of electric field.
X-axis.
Yes, direction of electric field due to a positive charge is away from the charge. So the field is along positive x-axis as well as negative x-axis. So this is the direction of field. Using this field, you're supposed to calculate the flux. We need flux through the cylinder. Just like the last derivation, we will divide the cylinder into three parts: first end, second end, and then the curved surface. Afroza, can you suggest the direction of this end one? What should be the direction of end one? End one, this is first end. This is cylinder. Like the cylinder is placed along y-axis. I'm not asking about the curved surface. I'm asking about the end. This end. The direction of area vector is always perpendicular to the area. So the perpendicular to the area will be upwards. The direction of area vector is always perpendicular to the area. Perpendicular to the area for this case is upwards. So for end one, flux phi1 is, this is the direction of area. This is angle between them is 90. So this is ES cos 90, which is 0. So through N1, flux is 0. Afroza, what about N2? The direction of N2? It's not upwards. The direction of area vector is outwards normal. It should be perpendicular as well as out of the cylinder. Now guess what should be the direction of this area vector? This one, this particular area. This is the cylinder. I'm asking on this surface. Yes, it should be downwards. So it's not just normal, it's normal as well as outwards, away from the surface. So the flux will again be 0 because your field is along x-axis. Angle between electric field and area vector is 90 degrees. So the phi2 is ES cos 90, it's again 0, that is second. Next, let's calculate it through curved surface. Flux through curved surface. So if you have a curved surface, then flux through this curved surface is integral of E ds. So for the curved surface, if I consider an element here, and I call this as ds, the direction of ds is along x-axis. It's very clear that E and ds are acting in same directions. So that means angle between them is 0 degree. It's E ds cos 0. So the flux is integral of E ds. Now, since this surface is a Gaussian surface, so field should be uniform. So we can take this E outside the integral. So it's integral of ds. Jubaina, what should be the value of this particular integral, ds? Jubaina? We did two integrals, like one surface integral for sphere and another surface integral for cylinder. If you integrate for a cylinder, then you will get the curved surface area of the cylinder. Say you are integrating over the curved surface of cylinder. So if you integrate over the curved surface, you will get curved surface area. What is curved surface area of the cylinder?
Pi r, 2 pi r square.
2 pi r L. This is curved surface area of the cylinder. So if you're integrating over the curved surface, you will get 2 pi r. Right. Now, in the next step, let's calculate total flux. Let's calculate total flux. So the total flux would be the sum of flux due to first surface, flux due to second surface, and flux due to third surface. That's the total flux. So due to first surface, flux is 0. Second surface, flux is 0. Third surface, flux is E into 2 pi r. So that is the total flux through the cylinder, which is E multiplied by 2 pi r. That is equation number. You can also calculate this flux using Gauss Law. You can Gauss. So Gauss Law says that phi is Q enclosed divided by epsilon. So that's equation number 5. Okay, Fatima. What's the total length of the wire? Fatima. What?
Infinity.
Yes, the total length is infinite. What portion of the wire is enclosed by the cylinder? What length of the wire is enclosed by the cylinder?
L.
L. So this Q enclosed is basically Q enclosed is charge on length L of cylinder. Length of wire. Because charge is distributed over the wire, not on the cylinder. So we can write this lambda as the charge divided by length. So we can write linear charge density is Q enclosed, and this Q enclosed charge is on length L. So I can write this lambda as Q enclosed L. Next, you can write your Q enclosed as lambda L. That's equation number 6. You can easily substitute 6th and 5th. On substituting 6th and 5th, you will get that your flux is lambda L over So this is flux due to long wire. This is equation number 7. Next, you can compare 7th and 4th. In equation number 4, this equation number 4 and 7, we are calculating the same flux. But the approaches are different. In 4th, we calculated flux using definition of field. But in 7th, we are calculating flux using simple Gauss Law. So, but in both equations, we are calculating the same flux through the cylinder. So we can equate 4 and 7. When you equate them, you will get E multiplied by 2 pi RL, which is lambda L over epsilon. This L will cancel this L, and you get that E is lambda over 2 pi epsilon naught. So this is electric field. E is lambda over 2 pi epsilon naught. So you can say that electric field due to this long wire is inversely proportional. This is inversely proportional to the separation from the wire. And the direction of field is perpendicular. So in vector form, yes, Fatma, usually this derivation comes directly in the exam. Usually it's a 3-marker question. So in vector form, this electric field E is, it's lambda over 2 pi epsilon naught R. Today I will finish chapter number 1. So by tomorrow I will share an assignment based on your previous year questions, the type of questions that has been asked in your exam. So you'll get a good idea of the type of questions that can be asked. So if I plot E versus R graph, this is R and this is electric field E. So the graph will be hyperbolic graph. That means on increasing R, the value of E will decrease. Just note this.
Sir, R is position or radius here?
R is always position. It's separation from the wire. There R is separation from the wire. And if you talk about cylinder, then this is radius of cylinder. But actually, this is separation from wire. Let's solve a numerical on the same concept. Let's take two long wire. Having linear charge density lambda 1 and minus lambda. The linear charge densities are lambda 1 and minus of lambda. We consider a point here. This point is at a separation T from both the wires. We have to calculate electric field at T. So at P, both the wires will generate electric field. So first of all, we take direction of field at P due to both the wires. So first wire is positive. So field at P due to first wire, let's call this as wire number 1 and this as wire number 2. So the direction of field is simply away from the wire. So it's acting away from the wire, that's E1. Due to second wire, the direction of field is towards the wire. This is the direction of field due to second wire, that's E1. Both the fields are acting in same direction, you can easily act it. So net field at P. So the net field at point P is just vector sum of E1 and E2. For the net field at P, just vectorically add E1 and E2. E1 is lambda 1 over 2 epsilon naught D. The direction is along x-axis, so let's put an I cap. Due to second, that it's lambda 2 by 2 pi epsilon naught D. So your pi is missing. It's 2 pi epsilon naught. And again, the direction is towards positive x-axis. Let's put an I cap. Next, you can just take common this I gap by 2 pi epsilon naught is common. In fact, D is common. You are left with just lambda 1 plus 1. In the same method, you can calculate field in this region or in this region, the way we have done for infinite regions. Now, when we talk about sphere, we can divide sphere into two categories. We can have two types of sphere. One sphere where charge is distributed only on the outer surface. Charge is distributed only on the outer surface. Charge distributed on outer surface. Distributed on the outer surface. Let's say the radius of the sphere is capital R. So you have some charge Q which is distributed, uniformly distributed on the outer surface. The examples of this type of charge configuration include if you have an hollow sphere. Now since sphere is hollow, there is no material inside the sphere, so charge will distribute only on the outer surface. It could be hollow conducting. It could be hollow non-conducting. It won't matter if your sphere is hollow, whether it's conducting or non-conducting, you will get same type of charge configuration. It could be hollow conducting or it could be hollow non-conducting. This could also be a solid conducting sphere. This could even be a solid conducting sphere. So whether your sphere is hollow conducting or a hollow non-conducting, or even if it is solid conducting sphere, even in conductors, charge is distributed only on the surface. If you take a solid sphere of copper and you charge that solid sphere, charge will reside only on the outer surface. Charge cannot penetrate a conductor. The second type of sphere could be a sphere where charge is distributed throughout the volume. Here, charge is distributed throughout the volume of the sphere everywhere. So, charge distributed throughout volume. Throughout volume of the sphere. And the example of these types of sphere includes solid non-conducting sphere. Solid non-conducting sphere. Because if you have a solid conducting sphere, then charge will reside only on the outer surface. The solid conducting sphere is this example. But if you have a solid non-conducting sphere, then charge will distribute it throughout the volume of the sphere. So these are the two types of sphere. This type of sphere is not included in CRT. It's not part of standard CBSE spheres. You have to do only this. This sphere is very important. You will study this sphere even in potential. You will study this sphere even in capacity. You need this particular sphere. Next, let's calculate electric field. Let's calculate electric field due to hollow conducting, non-conducting, or solid conducting sphere. Solid conducting sphere. So let's calculate first case one. If point lies outside the sphere. It's a very easy calculation. If point lies outside the sphere. Outside the sphere. So let's consider a sphere. This is the sphere. The radius of the sphere is capital R. Some charge Q is uniformly distributed over the surface of the sphere. We're supposed to calculate field over this point. This is the radius of the sphere. So we're supposed to calculate field at a separation R from the sphere. This is R. This whole is R. So to calculate field over this point P, the first step is choose an appropriate Gaussian surface. So you can easily guess that if your charge distribution is spherical, then your Gaussian surface should be a sphere. So I consider a sphere of radius R. So this is my Gaussian surface. This in yellow color is my Gaussian surface. The radius of the Gaussian surface is small. So consider a spherical Gaussian surface. A spherical Gaussian surface at point P. So at the point P, we have considered a spherical Gaussian surface. So first of all, let's calculate flux through the surface. Flux through Gaussian surface. So through the Gaussian surface, the expression of flux will be just fair, so we can use closed integral. It's closed integral of E dot ds. C is a positive charge. The direction of field is away from the charge. If I consider a small element here, then the direction of small ds elements again outputs. So E and n cap are acting in same direction. So you can simply take that your flux is its closed integral of E ds cos 0. Next, you can take this E outside this integral sign. So this is E. It's closed integral of ds. You can integrate this ds over the entire Gaussian surface. You will get phi is E into 4 pi r square. Remember, I'm not integrating on the surface of sphere. If I would have integrated on the surface of sphere, then area would be 4 pi capital R square. In fact, I'm integrating over the surface of Gaussian surface. So that's why this is 4 pi small r square. That's my first equation. Next, we can easily calculate the same flux using Gauss law. So here the phi is, the charge enclosed is Q only. So standard Gauss law is phi is Q enclosed by epsilon naught. This is the Gaussian surface. Gaussian surface includes the complete sphere. So you can say that your Q enclosed in this particular case is equal to Q only. So the phi is Q over epsilon naught. That's equation. You can easily equate 1 and 2. If you equate 1 and 2, it's equating 1 and 2. If you equate 1 and 2, then you will get E 4 pi r square is q by epsilon. So we can write this E as the value of electric field is it's q by 4 pi epsilon naught r square. So your field is inversely proportional to r square. This is the value of electric field. E is inversely proportional to r square. So see, the expression is same as that of a point charge. That's why in the first lecture of Coulomb's law, I've written that Coulomb's law is very easy, either for a point charge or for a sphere. So the behavior of sphere is just like a point charge. That's why the result of sphere and point charges will always be same. The second is if point lies on the surface of sphere. Can you guess the radius of the Gaussian surface now? If point lies on the surface of sphere, say if point lies here, the Gaussian surface will coincide with the surface of the sphere, right? Because you will take a Gaussian surface which is passing through the surface of spheres, it is passing through the point. So if I call this as equation number 3, so here small r would be equal to capital R. The whole calculation would be same. Just instead of small r, you will use capital R. So on the surface, you just substitute small r equal to capital R in 3, and you get electric field on the surface is q by 4 pi epsilon naught capital R square. This is the expression of field. Just one more thing. Let's say this is equation number 4. Fatma, can you calculate sigma here, surface charge density of sphere? The charge over the sphere is q, the radius of the sphere is capital R. So Fatma, what is the surface charge density of the sphere, the value of the sigma for the sphere?
Q enclosed by the area.
And what is the area of the sphere? Q enclosed is basically q.
4 pi r square.
Small r or capital R?
Small r.
No. Charge, where is this charge distributed? It's distributed on Gaussian surface or it's distributed on sphere? Fatma?
Yeah.
Sphere, and what is the radius of sphere?
Capital R.
So it should be q by 4 pi r square, not small r, right? This is equation number 5. If I substitute this 5 in 4, means instead of this q by 4 pi r square, I use sigma. Jubaina, what should be the value of field on the surface? If I use this 5 in 4, this q by 4 pi r square, if I use this as sigma, then what should be the value of field on the surface?
R square, sigma by epsilon.
This is the electric field on the surface of the sphere, sigma by epsilon. So you can either write this in terms of q by 4 pi epsilon naught r square, or you can write this in terms of sigma, q by epsilon, sigma by epsilon. If point lies inside the sphere, if point lies inside the sphere, if point lies somewhat here, inside the sphere. Now, can you guess, Afroza, what should be the q enclosed, value of q enclosed now? The point is inside, your Gaussian surface is inside. What should be the value of q enclosed now? Okay, just check. Where is this charge distributed? This charge is distributed on the surface or inside? This is distributed on the surface, not inside the sphere. The whole of this charge is distributed only on the surface, not inside the sphere. So if I take a point inside the sphere, then the charge over that point is 0.
0.
It could be 0. If I consider a point inside the sphere, then the charge inside this point should be 0. Q enclosed should be 0 in this case. If Q enclosed is 0, that means electric field inside the sphere is 0. So if you consider field inside the sphere, then electric field inside the sphere is always. The next is you're supposed to plot E versus R graph again. But now, why it is 0 again? Afroza, where is this charge distributed? The charge Q. This charge Q is distributed only on the surface of the sphere, right? If this is the sphere, then whole of the charge is distributed only on the outer surface. If I consider a sphere inside it, there is no charge inside the surface. That's why Q enclosed 0. There is no charge inside the surface. All the charge is distributed only on the surface, outer surface. Now the next task is to plot E versus R. To plot E versus R. This is R, and this is E. This is R equal to capital R. R equal to capital R means your point is on surface. R is less than capital R. So what you understand by R is less than capital R? This point is inside or this is outside? If this is the surface of the sphere, if I'm saying that R is less than capital R, this point is inside the sphere or outside the sphere? This is inside, less than R, less than capital R. The radius of the sphere is capital R. So if I'm saying R equal to capital R, that means on the surface. If I'm saying R is less than capital R, then point will lie inside. And if I'm saying that R is greater than capital R, then this point will lie outside. Okay. Now let's plot the graph. What is the value of field inside the sphere? Inside your electric field is 0. So this graph will be parallel to x-axis since value of field is 0 here. It's 0. On the surface, it increases. On the surface, the value of field increases. It becomes sigma by epsilon naught on the surface. And then what outside? Outside, the field varies as 1 by r square. Means as you increase distance, value of field will decrease. So outside the sphere, this will go. This is inside and this is E outside, which is inversely proportional to r square. So this is 0. Then field increases on the surface, then it again decreases outside. So this is how we plot E versus R. And these are very famous 1 marker and 2 marker questions. Plot E versus R graph for a straight line. Plot E versus R graph for a sphere. You can even use plot graph for the sphere for potential and capacitance of the sphere.